All right, well, welcome to the last day for you and for me. So we're going to do fluorescence today. So remember, my original title was Quantitative Absorption and Fluorescence Diagnostics, basically quantitative laser diagnostics. And so the most quantitative usually is absorption, but fluorescence is in fact absorption followed by emission. So fluorescence builds on absorption. And so we're going to spend all three lectures on fluorescence today. There's some theory for fluorescence, just like there is theory for absorption. And it's based on a very simple model. I call it the two-level model. So in the first hour, we'll spend a little time on the theoretical underpinnings of fluorescence, but it helps to know it's absorption followed by emission. Therefore, the basic parts about the absorption and the line strength and that sort of thing carry over directly. So I'll give you a little bit of a background, talk about the experimental setups, work my way down to some modifications to the simple two-level model. So it's kind of like when we did absorption. Even though there are many states that might interact optically, we can think about it just in terms of two and get the theory that we need. And so we'll always have some sort of energy level diagram like this that I'll talk about. Okay, so what is laser-induced fluorescence? It's really laser-induced spontaneous emission. So remember, we have the Einstein A coefficient, which is a number, probability per second of spontaneous emission. And we call it spontaneous because you can't say exactly when it's going to happen. You can only talk about statistics. And once absorption takes place, what happens to that absorbed photon? The molecule is in an excited state. It may wish to return back to its earlier state. How does it do that? It can do it by emission of light, or it can do it by a collision. And it turns out that the complication of fluorescence is this competition between these two processes and trying to understand their relative importance. So it's really a multi-step process. It's not an instantaneous process. So whereas we talked about the time scale for an electron to change orbit very fast, essentially zero time, so you can think of absorption as being instantaneous, fluorescence is delayed because that spontaneous emission may occur at any time, and it may happen that there's a collision that takes a molecule into another excited state before this happens. So it's delayed, not instantaneous. So we typically would be using a laser. It doesn't have to be a laser. In the earlier days, people used other types of light sources. Virtue of the laser being that we probably can go between specific quantum states because the monochromatic light is spectrally narrow. Once the molecule is here, it has choices. It can emit from any one of these adjacent states that might be produced by a collision. So the laser-induced fluorescence is that light which occurs later due to spontaneous emission. And now the thing is, this may occur from different states. So if this is a molecule, or even if it's an atom, but especially if it's a molecule, there will be some nearby states, rotational states, because remember, spacing of rotational states is small. So it may be rather easy for any collision to take a molecule from this state to this state before the emission occurs. We know about how long we're going to have to wait because the average length of time is going to be 1 over A. A is the Einstein A coefficient. So if that number, that average lifetime is comparable to the time for collisions, then there's some equal probability that there'll be a collision taking a molecule to another internal state before the emission takes place. So all of that light would be called laser-induced fluorescence. Why is it this of interest? Well, for combustion applications, the primary reason is that this is a way of getting spatial resolution in our measurements. So whereas line of absorption is line of sight, and we always have to worry about whether it is uniform along that line of sight, the fluorescence can be monitored at some angle. So we have light coming in, perhaps formed into a waste, and then expanded again. And rather than make our observation here at the end of that observation length, we'll look at the light that's emitted at right angles into some solid angle omega with some lens or collection optics of diameter d onto some kind of a detector, which might be a single point detector, it might be a photomultiplier, it might be a two-dimensional detector. All of that's fluorescence. So you can begin to see that this is the way to get spatial resolution in a measurement. We have the same situation that we've had before, is that we might think about scanning across an absorption line or we might have a laser that's spectrally broad compared to this absorption line. But if we were to do that scanning, we would see the laser fluorescence would generally follow, but possibly with a time delay, the absorption profile. And that's kind of a powerful idea, that if you could do spectrally scanned fluorescence, spectrally scanned absorption and monitor it in fluorescence, you have a new diagnostic idea here. So we try to do that sometimes at Stanford. Much of the same as the 2F ideas I talked to you about. Notice that the fluorescence is 0 in the wing, so only when you're in the vicinity of a line do you get a signal. So it's always very convenient when you have a 0 baseline to work with, rather than some sort of a offset signal. Okay, so this can be species specific, and for people who might be contemplating Raman scattering, the fluorescence signal is quite a bit stronger. So that's an advantage. Of course, there's a disadvantage to everything as well as an advantage, but there's a potential big advantage to get spatial resolution in an absorption measurement. Now, we can be using this to monitor multiple products. We might be interested in the number density in a particular quantum state, which is essentially what happens when we're doing absorption. We measure the number density in a quantum state. And then if we understand the Boltzmann statistics, we can go back to the total number density. So generally, we might use this technique to measure temperature, species concentration, pressure, velocity, using the same ideas that we had. So it's really helpful to think of fluorescence as absorption followed by emission. There's a lot of species that can be measured, and I just listed here some of the ones that we work with. Now, so in order to get this fluorescence, we have to have absorption. So we're not yet giving you a way to measure molecular nitrogen or molecular hydrogen because they don't have convenient absorption spectra. So we have to deal with species that do have absorption spectra. For the most part, fluorescence is done in the visible and the UV. Very few people have tried to do this in the infrared, but my group is one of those, and I'll come to that this morning. So for the most part, these are electronic transitions. So we might call them rovibronic. But it's possible to do some big molecules, and we're going to see that we use these big molecules for tracing flows, and we'll come back to that a little later. Now, actually, some of the earliest work with fluorescence was done with atoms. So if you're detecting atoms in, say, a flame, sodium, potassium, arsenic, lead, whatever, the same processes apply, and you can detect very small quantities. Why? Because the Einstein A coefficients are large. That means the absorption is going to be large, and it means that the probability of emission is large, and so you're going to get the strongest fluorescent signals for those molecules that have large oscillator strengths. Large atoms are molecules that have large oscillator strengths, and that is particularly true of atoms. Remember, it's the atoms, like sodium, that have the closest to a free-moving electron. Go to a molecule, electrons are confined, the oscillator strengths are smaller. Okay, so we have what we'll call essentially instantaneous laser absorption between some arbitrary levels 1 and 2, for which there are allowed transitions. But that's a line of sight idea based upon the difference or the ratio of the incident and the transmitted light. Fluorescence, then, we have the instantaneous absorption followed by the delay, where there may be changes in the upper quantum state before the emission takes place. Of course, that means that the emission may take place at different wavelengths, because each time you change into one of these states, and if it's a molecule, let's just say it's a diatomic molecule, you may have from each one of these states P, Q, and R branch transitions. So one color might produce many colors, because the wavelengths from each of these adjacent states, if populated, are slightly different. Anyway, it's not instantaneous, but you can think of it as absorption followed relatively quickly by spontaneous emission. Typically executed by looking at 90 degrees to get the spatial resolution that you're interested in. You can use either CW or pulse lasers, but in most cases people use pulse lasers. Why? We're going to find out that the fluorescence process is actually fairly weak, because only a fraction of the absorbed molecules in this small length undergo fluorescence. And of those, only a small fraction are collected because we have a limited collection angle. So we're going to find that it's a weak process, even though it's much stronger than Raman, it's a weak process. So how do you overcome it? You send in more photons. So you get a pulse laser which has a short burst of a large number of photons, in order to generate the signal that you care about. So I'm going to give you a little bit of history. It's nice to think about how long this has been under development. Lasers were invented in the early 60s. They were usually fixed wavelength solid state lasers. An important development was around 1966 by Schaefer, I believe he was in Germany. And this was a flash lamp pumped dye laser. So lasers you have to have some sort of energy going in, and oftentimes this is a flash lamp. So there's a bright, intense, like a flash lamp on a camera. There'd be some sort of an intense burst of light, which is absorbed by something. In this case, it would be a dye, an organic dye. And it would usually be a stream. It could, in the early days, actually, it was a little cuvette, just a little glass chamber containing specific dyes. And the dye would have the property that it would absorb that light, absorb photons, be produced in an excited state. There'd be some collisions, and then that dye would spontaneously emit. Usually that means that it's going to emit with photons of lower energy, longer wavelength. Once the dye is emitting, and the dye is emitting over a spectrally broad range, you can imagine that you would find a way to constrain the emission to narrow regions. And you would also find a way to tune the wavelength. So the dye would emit over some broad spectrum. That's the property of a liquid. But you could then selectively pick from this range of wavelengths and make it tunable. So that was a big advance a few years later. Tunable. Actually, the first ones were tunable pulse dye lasers. There was an important development to getting a tunable CW dye laser. So at that point, it was possible to pump with a high power, typically argon ion laser. So an intense laser, those were available. In fact, they're still available, they're still used. So you put in typically kilowatts of electrical power and eventually convert this to watts of laser light, which could then be used to pump a dye laser, which could be tuned. So it's the dye that gives you the tuning capability. About 1980, people learned how to frequency double this. So this CW doubled means whatever this wavelength was, we would have it. So having the wavelength means doubling the frequency. So you frequency doubled with a nonlinear crystal, and now we have tunable radiation in the ultraviolet. So the flash lamp was probably somewhere in the near infrared. The dye is somewhere in the visible. Frequency double, you get down into the UV. So that was about 1980, and we had one of the very first ones in my lab. Now there's been some advancement in the types of pumping of these lasers. So now the common way to do this would be with a particular, rather than flash lamp, would be with a neodymium YAG laser. It's neodymium yttrium aluminum garnet. So it's a solid state material which, when exposed typically to a flash lamp, emits light at 1.06 microns. So it's a fixed frequency pump laser with pretty good efficiency. So electrical energy goes into the flash lamp goes into the solid state device, out comes 1.06 microns, then it goes into some frequency conversion device. So there's stages of these lasers in order to get to what we want, which would be perhaps some tunability. Another powerful laser source is an excimer, and those are also fixed wavelength devices, but they happen to operate down into the UV, and so they can be used to pump dye lasers. So the dye is, for the most part, the way we get tunability, and that's because the emission spectrum of the dye is broad. You'll see more about that later. I was always been interested in trying to do wavelength scanning, so you've seen the power of being able to scan across absorption lines when we talk about tunable dye lasers. Well, it's possible to do this with a dye laser also, to CW laser, wavelength scanned, to do absorption or fluorescence in the UV. We did that in the 80s. An important development in 1982 was to, instead of making measurements at a point in the flow, and by the way, I should give credit, most of the early work on this was driven by analytical chemists who wanted to make measurements in flames or other devices. So they're interested in the ability to measure trace levels of atoms. So it's really a lot of the pioneering work was done for interpreting fluorescence by the chemists. But when it finally got to the combustion people and fluid mechanics people, there was always an interest in trying to measure it more than at one point. And that led to this first planar laser-induced fluorescence image, which was done in my laboratory in about 1982, so a long time ago. And then that was done in laminar and then turbulent, and so that particular strategy of PLIF is still in broad use today. So this was around in the 80s. There was single laser pulse imaging. We did OH, NO, temperature, velocity in that period of time. Along about 1990, we began to learn how to add tracers to the gases so that we could trace, understand and characterize mixing. So these were, tracers began to be used. Ketones, one category of tracers. Then there was some progression into supersonic flows. There was some progression into high pressure flows. Everything's harder at high pressures, harder to do the experiments, harder to interpret the results, but an extension to high pressures. I had a student and we began to look at infrared PLIF. That's a student who's a professor at Cornell now. So, and we're coming back to that again, so this is an interesting idea. Then there began to be a rapid development in lasers in which instead of having lasers that would, pulse lasers that would work at about 10 hertz or maybe 20 hertz, it became possible to have these lasers that would operate at much higher repetition rate. They're called pulse burst lasers for the most part. We learned how to measure CO2, and you might say, how can you do CO2? You told me that CO2 doesn't have a convenient absorption spectrum. Well, we found out actually that at high temperatures, above say 2000 degrees Kelvin, CO2 actually does undergo absorption in the ultraviolet. And that was a big surprise actually, along about then. That was a collaboration with the University of Duisburg. So then people began to use these pulse burst lasers together with PLIF, and so for about the last 10 years, there have been some high repetition rate PLF imaging going on. And we've come back to doing continuous wave, and I'll show you why that's a possibility, a possible advantage. Okay, so what's the typical experimental setup that you can that you can understand fluorescence by? We have some sort of a laser. It could be pulsed, it could be CW. It's typically formed into what's called a waist. Geometrical optics might tell you that you could focus to a point, but you can never really focus to a point. So you focus to the place where the beam is rather narrow, and you might trap this laser light so that it doesn't bounce around in your laboratory, or you might possibly measure the transmitted power. The fluorescence occurs into 4 pi star radians, but you would typically look at right angles, and you would collect as big a solid angle as you can. So this is starting to show you that one of the downsides of fluorescence is that it doesn't scale well to really large experiments. If the nearest place that you can locate your lens is some feet away, then this collection angle is going to be small. And so in the end, it's omega over 4 pi star radians that dictates what fraction of the collected light you get. And you want that to be as big as you can get. So this is most often done in modest size experimental devices, so that you keep omega large as possible. In the laboratory, we might capture 1% of the fluorescent light. Omega over 4 pi might be 1%. And then that light is brought to bear in some sort of a detector. It might be a photomultiplier. And now once we get to this point, you realize you have some options. You might have a broad spectral filter on this detector, or you might have a narrow one. This laser might be tuned, maybe it's fixed. So there's a lot of different options as to how to do the fluorescence experiment. If you you could look at a fixed wavelength by putting a narrow filter here, or you could actually put this light onto a spectrometer and then spectrally resolve it and look for the spectral distribution of the fluorescent light. You might scan the laser. That would be called an excitation spectrum. And then even though this has been arbitrary for a single point or multiple point, you could extend this idea to a two-dimensional detection with a CCD array. And that's pretty common now. There's another variation. If you have a pulse laser, short pulse laser, you might be interested in the time behavior of the fluorescence signal, because that quenching rate, that decay rate, contains useful information, as you'll see. So there's lots of variations of fluorescence. CW, pulsed, time resolved, spectrally resolved, and so on. And there are different advantages for each of these ideas. So if we look at some representative numbers here, you might find that this volume that you're looking at is about a cubic millimeter. You might compress this beam down to maybe 1/10 of a millimeter, but more often it might be a millimeter. Why do we care? The more molecules or atoms you have in here, the bigger signal you're going to get. If you make that too small, there's no molecules to probe, and the signal is going to be small. So there's some trade-off between the spatial resolution that you want, or that is satisfactory for your purposes. But the typical arrangement might be 1/2 to 5 millimeters. And so depending on what you're studying, if it's spatially uniform, then you can use a bigger number and have more molecules. If you're trying to study structure of turbulent flows, then you're going to have to make this number small. The solid angle collection omega is the lens area divided by this length squared. So that's just a number. And if you do this now in terms of the parameters, then you can introduce, if you wish, the F number of the collection optics. So you want a small F number. If the F number is 2.5, then omega over 4 pi is 1%. So that's kind of a typical representative situation in the laboratory. So that just means that whatever the fluorescence light emitted is, you're only going to get 1% of it. And you want to use what's called a small F number or fast lens in order to do the best you can. Of course, these small F number lenses cost more money, so sometimes there's a trade-off. Now we want to talk about the signal. So remember, once we are up in this level, the process that we're interested in is called spontaneous emission, A. And if there's only 2 levels, we'll draw it this way. So we'll pump the molecule up and then maybe watch this decay, which would be delayed. Let's imagine a steady situation, and let's keep track of the photons emitted per second. Actually, the photons collected per second. It's going to be related to the number of molecules in that measurement volume. So if you increase the number of molecules there, you're going to double the signal, you're going to proportionally increase the signal. It'll depend upon the probability per second of emission and the fraction of light that you collect. So it's really quite simple. Photons per second collected is the number of emitters times the probability per second times the fraction that you collect. If we want to write this in terms of the number density now, so I use a lowercase n, it's the number density in 2 times the volume that you're studying. So A is a number and it's known. Omega over 4 pi is known or can be measured. So these are known quantities. The volume also can be measured, calculated and measured. So the number of photons per second is directly related to the number density of molecules in level 2. But you may not be interested in the number of molecules in level 2. You're probably interested in the total number density of the species. So how do you get from N2 back to the number density of the species? The Boltzmann distribution. So you may have to know temperature in order to get to the number you want. Well, this looks pretty simple. Looks like we're done. So the power collected would be the number of photons per second times the energy of a photon, h nu. So the signal that you're going to collect depends on things that we know or are constants, and N2. So we ought to be able to measure N2. Well, what's the problem? We're going to see what the problem is here in a minute. We'll think of this as spontaneous emission, but remember it's distributed over time. If we had a pulse, which is the common configuration, we have a short pulse of light. Now we may be more interested in the total number of photons that come out in that pulse. So now instead of looking at N2 for that steady state case we looked at a minute ago, we're going to have to integrate over time. So now what we want to know is to capture the number of photons that come out, integrated over time. So it's really nothing more than N2 as a function of time, dt, because the volume, A, and omega over 4 pi are constants. So now we're going to get some sort of time integral of N2. Remember, we're using this pulse laser because we're going to need, when you have a pulse laser, you get a short burst of photons that's much stronger than the number you have in a CW laser. Well, this is now a relatively familiar diagram for you. When we introduced the Einstein coefficients, we had a diagram like this. So level 1 is an arbitrary level that's connected to level 2. There may be other levels, but 2 is enough to develop this model. So what are the possible processes? We have some molecules or atoms here, and we're going to pump them up to the excited state by absorption of light. Microscopic balancing tells us that if that's a possible process, the induced emission is also a process. So now it's driven by the light itself. Here's the fluorescence signal that we care about. That's the spontaneous emission, A coefficient. This is a intensity-dependent probability. So all of these are, as we did before, probabilities per second. So the number that are doing this per unit volume are N2. W21 has the units of seconds to the minus 1. It's also possible for a collision to make this happen. So Q is usually reserved for collisions. W is reserved for a radiation-driven process. A is the spontaneous process. So here we have radiatively driven absorption, radiatively driven emission. So these would be the 5 things we would have to think about in trying to model the behavior of our 2-level molecule. For the most part, if we're talking about energies that are rather large, this process is negligible. So we're talking about maybe, we're in the visible at 600 nanometers, that's 2 electron volts. The fraction of collisions doing this the rate of collisions doing this is negligible. So we can get rid of one of these. Can't get rid of this one. So the Einstein theory is the probability per second of going from 1 to 2. This is now then the absorption. If we go back to the Einstein theory, which was written in terms of the spectral energy density, which I'd like to immediately convert to intensity, is here. So this quantity basically is the Einstein B coefficient times the intensity of the illumination. And that's the line shape function. So we're back to probability per second of a molecule in 1 going to 2. It's linearly proportional of a molecule, so I haven't said how many there are, of a molecule. So it's B12 I nu. That's a number. You have to be careful about the units, but it's a number. That's your provided laser intensity. With the nu, it either means intensity at nu or it means intensity per unit frequency at nu. You have to be careful about that. Line shape function. So if the laser width is narrow, we have to have a line shape function. Okay, so that's the probability per second of this event. And we can do something similar for the other events. So it turns out that most lasers are spectrally, if they're pulsed, they're spectrally broad. So let's think about our absorption line here, having this shape. And then let's imagine that our laser is spectrally broad compared to the absorption line. So what does that mean? That means we're going to be providing light that integrates over that entire absorption line. And when in doubt, you assume that the absorption line has a width of about 0.1 wave numbers at STP. That's first order estimate. So if you buy a pulse laser, it might have a width of 0.5 wave numbers. So roughly speaking, that means the intensity is constant across this absorption line. That simplifies our mathematics. So the rate of going from 1 to 2 is what? It's the number in 1, because all of this is the probability per second. So it's the number in 1 times the probability per second, where I nu is now this average intensity. Average intensity. And this BI is usually written with a W. So the units of W are seconds to the minus 1. The number per unit volume going from 1 to 2 is the number in 1 times the probability of going from 1 to 2. Now, in a lot of cases, we will do what chemical kinetics people would recognize as a rate equation. We would write the time derivative in 2, consisting of a pump term, which produces molecules in 2, minus the loss terms. So the time derivative of N2 is the pump term of absorption minus the loss term. And the loss term now is comprised of the components, the induced emission, the collisional decay, and the fluorescence. And so the question we're going to be faced with is, what are the relative values of these 3 terms? When you have these rate equations and you're looking for a way to solve it, what are we after? We're after N2. We're after N2. because fluorescence is done basically in terms of getting to N2. The trick then usually is, it's not so much of a trick, but then we go from N2 to total number density with the Boltzmann equation, Boltzmann distribution. So the trick that's played is to take what's called the steady state approximation. In that approximation, we say that N2 dot is the difference between a large positive and a large negative term. And that so these two large terms are bigger than this small term. So we say, let's estimate this by calling it 0. So we approximate N2 dot with 0, and we solve for N2 from this equation. This does not mean that N2 is constant. It only means that N2 dot is small compared to the positive and negative terms. If you do that, you have an immediate solution for N2 that's called the N2 steady state solution, which is N1 times the ratio of the pump term and the loss terms. So that's pretty simple. So that just says that the thing that we're going to measure by measuring the fluorescent emission is nothing more than the number in the absorbing state times this ratio of terms. And this, if we knew the temperature, would be related to the total number density of that species. So this is looking pretty simple. Where's the problem? We have a simple solution for the fluorescence now. This would be what I'd call the entry-level model for fluorescence, the two-level model. It says that the steady state value of N2, and you've noticed I've taken time out of this now. This may apply at any time t, is nothing more than N1. And N1 is the quantity we'd really like to measure, because that together with the temperature gives us the total number density of absorbing species. So now from this simple equation, it turns out that there are two simple limiting cases. One is called weak or linear. One is called saturated. And you'll see what that difference is in a minute. Off to the side, it looks like I've written this relationship between the B's. That came to us when we did the Einstein theory. Remember that the degeneracy in level 1 times the B for going to 1 to 2 has to be equal to this in order to you do this by looking at equilibrium where all processes are balanced. And then you go away and you realize these are just probabilities. They don't know whether there's equilibrium or not. So that just means that W12 and W21 are related simply by the ratio of their degeneracies. Okay, the weak excitation limit now is that the induced emission from level 2 is weak. Basically that this term is small. And this is actually a pretty common situation. So if the laser power is low, then W21 is low. We can't throw out W12 because it's the pump power, it's the pump process. So even if W12 is small, because we're in the weak excitation limit, it's W21 that's negligible compared to these two. So the weak excitation limit is that for which W21 is much smaller than A plus Q. What's A? It's a number, probability per second. If the oscillator strength is large, this is the number like 10 to the 8th. If the oscillator strength is weak, it might be 10 to the 4th, 5th, 6th. What's Q? It's a collisional quench rate. It must be related to the collisional rate in the gas, which we know can be a very big number. I keep telling you that the collision rate of nitrogen molecules in this room is over 10 to the 9th per second. So this is a number that might be 10 to the 9th, 10 to the 10th. Here's a number that might be 10 to the 6th. And so we arrange for W to be smaller than that, and now but we're left with these two. So what are we going to do? So we're in this weak excitation limit that we can infer that N2 is much less than N1. We are barely disturbing N1, so that N1 is probably close to its initial value. In the limit of weak laser, we don't really perturb the distribution very much. We only excite a small fraction of the N1s. So as an approximation, we usually just say that N1 in this process is, we only have a two-level molecule now. So even though I keep telling you we're going to use the Boltzmann distribution, right now we really only have two levels. So N0 then would be the total number of molecules in our two-level system. So now we're done. We have N2 in the weak excitation limit is the number of molecules in level 1 initially times this simple ratio, where this is going to be a small number because we've made this a small number. So in the weak excitation limit, we can now substitute back in our solution for N2 and say that the fluorescent signal and the number of, that is the photons per second, is nothing more than the number density in 2, volume, probability, fraction collected. And if I insert that answer for N2 and rewrite the expression just slightly, my omega over 4 pi stays here. Here's my N1 volume. But I've substituted now W12. This was the probability of emission. So now I can interpret these signals, these terms in a new way. This is the photons absorbed per second, because W is the probability per second of absorption. Here's the total number of molecules in the measurement volume that are available to undergo absorption. This is photons absorbed per second. This is nothing more than the fraction of those absorbed photons which are re-emitted. This is the probability of emission divided by the total probability of decay and the fraction collected. So this is a simple way to think about it. Photons out are basically going to be photons in, fraction absorbed, fraction re-emitted, fraction collected. So A is a number. What's Q? Turns out that that's the biggest problem with fluorescence. So LIF in the weak excitation limit is directly proportional to the population density in the lower quantum level. And therefore, this is most often thought of as a species diagnostic, but it's possible to think of it as a temperature diagnostic. Another way to think about the absorptions is that the number of absorptions per second is the number of molecules times the probability of absorption. So here's photons per second, but now I'm talking about molecules and their probability. So you look at it this way, here's the number of molecules and here's the probability per second. So you can look at these fluorescence equations and get a physical interpretation. Now what's the other limit? The other limit is the saturation limit. Now W21 is large instead of small. And now if W2, in this case, again using these things again, if you use this, now we throw away the A21 and Q21. So N2 is N1 times this simple ratio of W's. But we already know that. So now N2 has this very simple interpretation. N2 is N1 times the degeneracy ratio. If the degeneracy ratio is 1, N2 equals N1. I've simply taken half the molecules and put them in N2. So if you shine a light in that's bright enough, meaning that it has the high probability of absorption, you will eventually reach a place where the excited population is nothing more than a fraction of the initial population. These become equal. So you take half of the N1s and put them in N2. Well, you may or may not have enough power to do this, but if you do, we have now a very simple relationship for N2 in terms of N1. We call that saturated. If we had a simple molecule where there are only two states, if we had such a case, we don't, but if we had such a case, then there'd be a simple way to relate N2 to the initial total number of molecules, N10. So in this saturation limit, you would have a relationship between the photons per second out, known collection volume, known A, known volume, known collection fraction, known A, known volume, known degeneracies, and you have a simple relationship between photons measured and the number you're after, which is the number density in the absorbing state. That would be great. What's the problem? It's not easy to saturate. It's not easy to bring in enough light that makes this happen. So if you're in between these two limits, and I'm just going to, you have access to these notes, so that you can solve these equations in the intermediate case, and you can have plots for how the fluorescent signal compares with its saturated value of 1, depending on the values of the B coefficients and so on. So anyway, there is a solution for intermediate, but the interpretation is a little trickier. So what are some typical values that we might look at to see how close we might get, how much laser power we might need to do these things? If we imagine that the A coefficients of interest range from around 10 to the 5th, which would be about the right number for, well actually it'd be about 10 to the 6th for the electronic transitions of NO or OH. It'd be about 10 to the 8th if we were studying sodium. So A is in the range 10 to the 5th, 10 to the 8th. If A is smaller than that, we usually cannot use this process. Z is the collision frequency. Excuse me, Q is the collision frequency, which is essentially Z, which would be the, I didn't say it right yet. Q is the collisional decay rate called the quench rate, which is approximately the collision frequency, which we did by hard sphere and came up with the N cross-section and mean molecular speed. Now, if we argue that this is the cross-section here, this is a relationship that's proportional to P over the root of T. Q is in the range of 10 to the 9th to 10 to the 10th at STP. So what do we see? If we looked at A over Q for OH at 1 atmosphere, we'd get a number of 10 to the minus 4. What does that mean? Well, it's essentially the quench rate. That means that you have to absorb 10 to the 4th photons before you emit 1. Actually have to absorb 10 to the 6th photons before you emit 100 so that you can capture 1. So all of a sudden this looks like a pretty inefficient process. I got to absorb 10 to the 6th to get 1 onto my photodetector. And my photodetector is kind of noisy, so I better collect at least 10. Okay, so now I got to absorb 10 to the 7th. That sounds like a big number. But it's possible with the pulse laser. So the fluorescence yield, the yield of fluorescence, which is the ratio of success to failure, is much less than 1, except when you go to low P. Because remember, the enemy, which is Q, scales with P over root T. So it's an inefficient process, but it's still better than almost everything else. Spontaneous emission for IR is much weaker. Why? Because we have small A values. Remember I did the example for CO fundamental, A coefficient was something like 0.03. It's terrible, but it might still work. So that's why for the longest time I think people never did infrared fluorescence. It looks like the A coefficient is impossibly small. But it turns out that the ratio of the Qs is different than we thought, and it turns out there's a possibility. But for the most part, people do fluorescence with electronic transitions, meaning visible in UV. Well, what is it going to take to saturate? What value of I do we need for B to be much greater than A plus Q? So what is the saturation intensity that we would need? So first we could ask, well, what if the Q is low, meaning if we have a low pressure? Then this I has to be greater than I over B. Then there's the other limit when we have high Q, which is high pressure. So you can look at these scaling relationships and you can work your way through it. And so if we took the case where Q is 10 to the 4th A, for example, if Q is 10 to the 10th, A is 10 to the 6th, Q over A is 10 to the 4, you can then solve for the saturated intensity in terms of the value of A, and you get 10 to the 4th here. And you can go through this and argue what the intensity has to be in ergs per square centimeter or joules per square meter for this particular case. But that doesn't tell us much yet. We need to look at some more details. So what is, if we call it, let's do this again now in terms of power. So it's easier to think about either the energy per pulse of the laser or the instantaneous power of the laser. So if we think of the intensity as the ratio of the power per unit area per unit frequency. So I sub nu now is going to have units of like watts per square centimeter per unit frequency. And we have to get some dimensions here. So we imagine that this width is about a millimeter. We imagine our laser line width is about 0.5. We put in this in terms of power. You can work your way through and convince yourself that it would take 5 kilowatts of laser power. Well, 5 kilowatts looks like a pretty big number. It's way too high for a continuous wave laser. But it turns out that if you take one of these pump lasers, which give out 1 to 10 or maybe even 100 millijoules in a 10 nanosecond pulse, if you do this 225 nanometers, or 300, and 1 millijoule would be achievable. That's already 100 kilowatts or a megawatt. That's the power of a pulse laser. So we solve this problem by putting in a lot of photons in a short pulse. So the instantaneous power is way more than 5 kilowatts. So we can't do this with a CW laser, but we can do it with a pulse laser. So it's possible to saturate within the limits of a two-level model. So we might say, we're done. No. Turns out that with atoms, it's possible to saturate. With molecules, it's not so easy. Why is that? That's because we have problems with the collisional transfer rates are high, and so we really, it's hard to saturate. Hard to saturate. So now we're going to look at this in the infrared, which is what we've done at Stanford. So let's now look at A and Q, which are the terms that we have to think about are A and Q. So now we're going to imagine, I didn't say that right. I said A was, I should have said A was 30. It's not 0.03, it's 30. A is 30, inverse of A is 30 milliseconds. So A is about 10 to the 1 to 10 to the 2, 30 for CO, for fundamental, strong IR. Now we have to decide, think more carefully, what is Q? It's the collisional quench rate. But it's really the transfer rate out of the upper state. And that number might be quite a bit smaller than it is it's quite a bit smaller than the overall collision frequency. So in fact, this VV rate, it's called, is more like 10 to the 5th instead of 10 to the 10th. So all of a sudden we just gained 5 orders of magnitude. So the point is that the fluorescence yield, which is the ratio of A over Q, isn't as bad as we thought. It could be in the range of 10 to the minus 3 to 10 to the minus 5, almost the same as it was for the electronic transitions of OH. So it became possible, we realized, to do this in the infrared. Still not done by, I think maybe the Swedish group of Aldane does this now, and we do it. Now we might want to look at the detection limit. So you'll say, this is nice, but what's the density of species that we can measure by this idea? So here's our signal again, integrated over time, because we're thinking about a pulse laser. We look at this relationship. Here's the definition of the terms. Now we're beginning to be specific. If we can determine the number density in the absorbing state, we still have to get back to the total number density of that species. Total number density of the species would be the total number density of the gas times the mole fraction of the species. And that's usually what we're after here, would be that number. Okay, so we can go back to the integrated signal and imagine now that, write it in terms of the pulse energy divided by the area and the frequency width. So you can define things this way, calculate then the signal in terms of this number density we're after, the length of the measurement zone. So sometimes you see length instead of volume. Why did we do that? It's because the volume is the area times the length. And so when you do things per unit area, you get rid of the A, and it comes out to be proportional only to the measurement length. So what is this? This is the fluorescence signal in the limit that A is much less than Q. And the answer is A over Q. B is a number, omega over 4 pi is a number, pulse energy, line width, length, number density. So the signal depends on the number of absorbers, the length of the volume, energy you send in, constant, omega over 4 pi, and Q. But we don't actually know what Q is right now. And that's the biggest weakness of fluorescence. Biggest weakness of absorption is whether or not it's uniform along the line of sight. Biggest weakness of fluorescence usually is that we don't exactly know what Q is. So we're going to do an example to show you what the detection limits are. And we'll do this in the weak excitation limit with a pulse laser. And so you have access to these numbers. So we'll take a pulse energy of, say, 10 microjoules. That doesn't sound like very much, 10 microjoules. It's 100 ergs. We take a pulse length of 10 nanoseconds. We take a laser line width of 1 wave number. I've rounded some numbers to make this easy. We take a number density of 5 times 10 to the 18th, which is essentially 1 atmosphere and 1600 Kelvin. We take a Boltzmann fraction of 1%. So in that example problem we did with OH, that took us an hour, I think we ended up with about 1% of the molecules in the absorbing state. So FEJ can be 1%. Take our measurement volume of a millimeter, by cross section. Basically, this is 10 to the minus 3 cubic centimeters. Collection angle of 10 to the minus 3, which would be F8 optics. Take some representative Einstein coefficients using an A of 10 to the 6th. What do you get? Put in these numbers. So we have it confined, we have it constrained. We know how many photons we're sending in. We know the region, the size we're looking at. We know all the parameters. And what do we find? We find a number 3 times 10 to the 7th chi. So the signal in photons would be 10 to the 7th times the mole fraction. Of course, the mole fraction is between 0 and 1. Now it's starting to look pretty promising. And so we have to know one more thing. Not all photons collected give photoelectrons. The quantum efficiency is the number of electrons that we can use in our detection circuit divided by the number of photons in. So the signal is, the number of photoelectrons is the signal in photons times its quantum efficiency. And roughly speaking, there is a shot noise limited relationship that tells us the signal noise ratio is going to be proportional to the square root of the total number of photoelectrons, which is photons times eta. So now if I put that substitution in, I say my signal noise ratio for my experiment is going to be square root of 3 times 10 to the 6 times the mole fraction. Still looking pretty good. So the signal noise ratio, if I took a signal noise ratio of 1.7, which would be kind of a minimum that I could accept, that would correspond to 1 ppm. Or in other words, signal noise ratio of 1 is 0.3 ppm. So all of a sudden this is looking pretty promising. Maybe this idea works pretty well. Maybe you can make non-intrusive measurements in a cubic millimeter volume in 10 nanoseconds with only 10 microjoules of laser energy. So it is actually sensitive because we kill it with a big burst of photons. Now you might say, that's good, but what about this? But I still have a problem because I don't exactly know what Q is. I can't make it quantitative. In the saturation limit, I get rid of the Q problem. I can go back through the same simulation, putting in numbers with the new relationship that no longer has Q in it. So we eliminate Q by overwhelming it with photons. When you do this, you end up benefiting by about a factor of 10. So you go through this and you end up with the minimum detection limit is about 0.04 ppm. You don't want a signal noise ratio of 1. Maybe you want 100. So, but that would still mean 4 ppm. So fluorescence has the potential for very sensitive detection of a species. The problem is that it is difficult to saturate if it's a molecule, and therefore you have to know Q. In saturation, there's no Q. In weak excitation, there's Q, A over Q. Okay, so that's kind of a summary. It's hard to saturate for molecules. We're often in the weak excitation limit. If you put in enough photons, you can get enough photons out. You can get good detection limits. It's hard to be quantitative. It's spatially quantitative, temporally quantitative, but to get the absolute concentration is limited by how well we know Q. Now, I've used the steady state approximation, and we have to ask a little bit about whether that's fair. If we have a laser pulse that might look something like this, and it has a width of 5 to 10, 5 to 20 nanoseconds, are we okay with this? How long does it take for the steady state approximation to apply? So we go back to our relationship, and here we have this expression for the number density in 2, depending upon these parameters here. And so in the weak excitation limit, here is our answer for the number density steady state number. The question is how does the time it takes to get into steady state compare with the pulse length of the laser? Is it fair to make the steady state approximation when the laser pulse length is so short? That's the question. So you can define a time characteristic. You can define a time to reach steady state. So here's the steady state number in the weak excitation limit. The way to think about this is, imagine we have a step change in I, and then let's ask, how long does it take to get into steady state? The steady state time is the final value of N2, given to us over here, divided by the rate of production of N2 when it's subjected to a step change in intensity. So if we define a characteristic time as the ultimate value divided by the rate of production. That's a characteristic time. And if you go through that, so we're basically imagining we turn on a pulse of light right here, and then we're building up the population at level 2. And then we might turn it off. How long does it take? So there's a time to go into steady state, and it'd be 1 over this number. And then this is also the decay time. It's a reminder that the decay process depends only on A plus Q because there's no more laser. So there's 2 limits. There's the weak excitation case and the strong excitation case. Weak excitation means W12 is small. In that case, tau is nothing more than 1 over Q. And we just looked at Q and said it's in the range of 10 to the 9th to 10 to the 10th. So the time to reach steady state is somewhere in the range of a fraction of a nanosecond. Depends on Q. So therefore, steady state relation holds up fine when you have nanosecond pulses. Someone asked me a question about short times. I'm not sure that I understood the question, but if you were to say, no, I've got a picosecond laser, can I still assume steady state? No, when you get down to times that are shorter than collision times, you have to invoke something called a density matrix in quantum mechanics. So that's a different domain. But as long as the times of interest are basically longer than collision times, you can get away with this approximation. So the steady state model, which is so simple, is applicable. If you go into the strong excitation case, where we're going to have a stronger laser pulse, you can imagine that the times are going to be shorter. Why? Because you're pumping so hard, you're pushing the molecules up right away. So in this case, where W is greater than Q, greater than A, tau is much less than 1 over Q, and is much less than a nanosecond. So the stronger the laser, the faster you get into this limiting case. All right, so what have I told you? We can use steady state analysis to solve for N2. If you know N2, you know what you need to predict the fluorescence signal. And the trick is how to relate it back to the quantity you care about, which is the gas is sitting there, you want to know what it is. You send in light, you produce N2, you measure that emission, you solve basically for N2. How do you get to N1? Well, you go to the 2-level model that says that the steady state value of 2 is related to N1. This is what you're after, the number density in 1. But you need to know these W's and Q's. A is known, W's are known, because remember, if you know A, you know the B coefficients. And there's these 2 limits. The fluorescent signal then is, for our 2-level model, the fluorescent signal is the thing we're after, initial concentration N1, times stuff that we know except for Q. Killer is the fluorescence yield. What is the fluorescence yield? We know A, but we don't know Q. Why? Because it's a special kind of collision. It's the collision that takes you from 2 to 1. Not all collisions do this. Just like we have inelastic collisions and elastic collisions. They're different. Elastic does not change the quantum numbers. Inelastic does. But change the quantum number from what to what? Not so easy to say. Saturation limit is nice because there's no longer any Q. So the saturation limit is great if you can do it. But there's a problem when you send in really intense light, and that's called hole burning. So if you send in intense light, you begin to saturate perhaps just one velocity class. Remember, molecules have different speeds, and you might saturate some velocities and not others. So that's a problem. I'm not going to talk about it. Now here's a help. Here's a help. It's an issue, and we have to understand. If you have a molecule now, it's a multi-level molecule. You pump from B double prime, J double prime to B prime, J prime. If nothing else happened, you now could have light coming back down at P, Q, and R, say. But we can have a collisional quench rate This is a quench collision. These are vibrational transfer collisions. Here's a rotational transfer collision. So the inelastic collisions are 3 types: J changing, V changing, electronic state changing. So now all of a sudden what's Q? Which Q are we talking about? If you decide that the important Q is the electronic Q, you have to recognize that if this molecule is here, it may do this, or it may do this, or it may do this. And at each time step, it may emit. So you have to track the molecules. Initially, you can do this, or this, or this, or this. If you take a rotational change, go over here, you now have, it's like a sequence. Now you get the same choices. Once you change J, it's like a new ball game. You get a new set of choices to do A, or another Q, or one of these. So these are multi-level effects that we have to think about. And it turns out then this leads us to 2 ways to do this experiment. We pump from one state to another. If these processes take place, the emission will occur at different wavelengths than if it's right here. So you could collect only this light, thinking that all of these, if they fluoresce, will occur at a different color. Or you could decide that you're going to use a spectrally broad filter that captures all of the light that comes out, regardless of what happens on the way. It might go to here, different J, eventually it can emit, but you have a broad spectral filter and you collect. That's called broadband collection. There's 2 limits. If you do narrowband collection, you collect only from here. Then the rate equation has A for that set of A's, that's the sum of those A's, plus all of these terms. So in that weak excitation limit, the steady state concentration is, the relevant Q is the sum of the Q's, the sum of all Q's. That's a big number. If you go to broadband collection, we say, I don't really even care if this happens. I'm going to collect A. In that case, the sum of the Q's is that which removes the molecules from the possibility of emission. Only QEL does that. So this leads us to have an important point that you have to carry with you. I don't know if it's on the next slide or not. Okay. Basically then the fluorescence signal is the number density in 1, this is the weak excitation limit, number density in 1 times things we know, times A21, which we know, divided by A over A plus Q effective, where Q effective now is basically the transfer rate out of the emission bandwidth. So if you define this narrow bandwidth, Q is going to be bigger. If you define, if you capture all this light, Q is these rate coefficients don't come into play. So basically, Q is the rate of transfer out of the collection bandwidth. That's a very important point to carry with you. I'm going to skip over this. Am I doing that time? Okay. I think am I over already? I think I'm over already. All right, so I'm going to skip over. There's some simple models. We modify this. Okay. Next lecture. I want to move towards some examples. Spatially resolved with signal from a point or a line. We can do this. If we do it in a plane, it's called planar laser-induced fluorescence, and I'm going to show you some example cases. Sorry, it looks like I went over about 7 or 8 minutes. See you in about 10.